Hi everyone, I'm Micaiah and this is my report for Lab 3, Magnetic Field of a Bar Magnet. Here's an overview of the lab. The purpose of this lab is to measure the distance dependence of the magnetic field due to a bar magnet. The physics principles involved in this lab are the Biot-Savart law for a magnetic dipole and the superposition principle for magnetic fields of the Earth and magnets. My results are mu is 0.88871 ampere meter squared. N equals negative 3.1741. The expected value is n equals negative 3. My percent error is 5.8%. I'll quickly recap the lab procedure. I downloaded Teslameter, which measures magnetic fields. Then I located the sensor in my phone. First, I compensated for magnetic north by finding where the x component was nearly zero, and I aligned my meter stick with the bottom edge of my phone. Then I oriented the magnet on the east-west axis and positioned my phone perpendicular to the magnet. Then I moved my phone vertically to find the max x and min y, both absolute values, and placed the tape on my phone. Then I rotated my phone 90 degrees to become parallel to the magnet, and again I moved it vertically to find the max y and min x, both absolute values, and placed a piece of tape on top of the first piece. The intersection closest to the front camera was the sensor. Onto the experiment. With the sensor parallel to the magnet, I found and measured the distance with the magnitude of dx for the following values listed. Then for the second half, my phone was perpendicular to the magnet and I found dperp, where the net magnetic field was 100 microtesla, and measured by Earth. Then I moved my sensor vertically the distance I found along a perpendicular meter stick and measured the x, y, and z components of the magnetic field. Keep in mind that after each trial, I zeroed out the x component. I observed during my experiment that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Here's my data recorded in Excel. After I finished plugging in all my measurements, Excel found the averages and recorded them in this graph. With my data, I was able to find n, which was the slope of the graph. Since the y-intercept was lmk, I was able to raise e to this value to get k. I set the b bar and the magnetic field of the dipole equal to each other to find mu. For the coding section, I added my data and created a function to measure the magnetic field at different locations, the general formula of the magnetic field of a dipole, as well as creating arrows to visualize the field at each location. Here's the key. The magnet is in the center. The on-axis arrows are in orange. Perpendicular arrows are cyan. And the 45-degree arrow is magenta. Here's a clearer view of the 45-degree arrow. When compared to my data, the D's were relatively close, but the magnetic field components were slightly off. I'll conclude with some final thoughts. If I didn't compensate for magnetic north, then the results would have been skewed, since the Earth's magnetic field would also contribute to the magnetic field of the bar magnet. If I had two identical magnets, I would expect the magnetic field to increase by about as twice the value of the individual magnet due to superposition. Finally, the lab helped me to visualize magnetic fields of a bar magnet, as well as detect the interference of magnetic fields. I was successful in understanding distance dependence of magnetic fields and finding and calculating values for n, k, and mu. Thank you so much for watching, and I'll be back with more physics fun.